Right, good morning everybody. I circulated everybody yesterday with a typographical error on the problem set, so I've just put it up on the screen there. It's actually, let's zoom that a bit. It's in question 3.4. If you look at the conditions attached to that, they don't make a lot of sense. So it's supposed to say f of u equals sine k u if minus 2 pi is less than or equal to k u is less than or equal to minus pi, 0 otherwise. And then the next one is also incorrect. It's even worse, if anything, because it's nonsense. Whereas this one was internally consistent but wrong. But this one should say if pi is less than or equal to ku is less than or equal to 2 pi and 0 otherwise. So I'll post an updated version of the problem set hopefully later today. And that's the, I was giving tutorials on this sheet yesterday. That's the only mistake that I found. So I hope that's the only one. So today I want to do two things. I've been fairly scrupulous about timekeeping up till now, but I will allow myself to run up to 12 o'clock if we're doing something useful at 5 too. So yesterday we talked about reflection and transmission of waves and energy at boundaries, and I started by criticizing the form of the boundary that we were going to use, which was an abrupt transition from one string to another. And I said you need something on the boundary to hold the two strings together, since they are, after all, under tension. So it would be more realistic if we put a mass m on the boundary. And that changes things not a little, and that's the problem I want to solve now for reflection and transmission at that kind of boundary. So first of all, it changes the boundary conditions, or at least it changes one of them. I'm going to write the boundary conditions in a different way. This time I'm going to write them as delta y equals y2 minus y1 equals 0. So I wrote that yesterday as y1 equals y2. I want to write them as changes across the boundary today. So the string is continuous at the origin. So this is the point x equals 0. Incidentally, if you take the boundary at a different point, A, so you don't set it to 0, that does affect the form of the reflecting coefficient in an entirely non-physically meaningful way, because it has the effect of changing the phase of the reflected wave relative to the transmitted wave, shifting the boundary to A, and then the reflection coefficient has to change to remove that. So that the reflected wave is the same as it always was. So the choice is, it's actually not trivial putting the 0 at the boundary, but it does make the mathematics easier. And the other one is delta dy by dx equals dy2 by dx minus dy1 by dx, and that is not 0, it was yesterday. So let's draw the string with the mass on the boundary. So here is y2, here is y1 on the other side of the boundary, and as I've drawn it, that change, if you just imagine pulling on that string, you can see that what you're doing is you're flicking the mass upwards. So that's exerting an upwards force on the mass, and that's what we need because the mass follows the motion of the string and needs accelerating, and therefore that is equal to m d2y by well, strictly speaking, it's a total derivative, d2y by dt squared, where y is either y2 at 0t, or equivalently it's equal to y1 at 0t. So it's the y on the boundary, and you can take that either to be y1 or y2 because this condition sets them both to be the same. So if we put down the same incident and reflected waves as we had yesterday, so on the left side of the boundary we have e to the I omega t minus k x, and we have a reflected wave plus r e to the I omega t plus k, and that's going to be k1 x. And on the transmitted side of the boundary we have t e to the I omega t minus k2 x, and then I put that into the boundary conditions, and I get, for the delta y boundary condition, I get t minus 1 minus r equals 0. And for the other boundary condition, I get minus I k2t, and then I get plus I k1 minus I k1r equals, and on this side I'm going to use this form of the, I'm going to use y2 because it only has one term instead of y1. So on this side I've got the second derivative of this on the boundary, which is minus, multiplied by m, minus m omega squared t. So those are my two boundary conditions, and I'm going to cancel through a minus I from there and put an I in there, and then the minus I from that will turn that into a minus. So I'm going to multiply the first one by k1, 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 and I'm going to add the equations. So I get k1 plus k2 t, and this is the kind of board algebra I'm not really very good at, so let's cross out terms as we go, and then we'll get so we're adding, so that's minus 2 k1, and that gets rid of those two, minus k1r plus k1r, those go, and that's equal to minus I m omega squared t. So I've eliminated r, and I've arrived at if I take 2k1 over this side, and wait a minute, something dreadful happened there, didn't it? That was a minus there originally, because I was adding. So if I take that over the other side, I get k1 plus k2 plus I m omega squared t. Now, something went wrong, and the place it went wrong was here, because it's the tension times the gradient that gives the force, not the gradient on its own. So that introduced a factor of the tension there, and here it will introduce a factor of tension there. There. So, and presumably on the other side as well. Right, so that I think is dimensionally correct. So we now get T is twice the tension times K1 divided by T times K1 plus K2 plus IM omega squared, which probably to make it look a little bit more like we got yesterday, will be 2K1 divided by K1 plus K2, which is what we got yesterday, but then in addition we get plus IM omega squared over the tension. And that is T. And the important point about that is that it's complex, which means that the reflected wave is phase shifted, and I'm not going to, obviously I could back substitute that into the first equation and work out what R was. I'm not going to do that little piece of algebra because I'll stop while I'm ahead. So so it's phase shifted, which means that reflected wave, the transmitted wave and the reflected wave are both phase shifted relative to the incident wave. It also means that if you try to do the solution with an arbitrary input wave, an f of put an input wave of f of t minus x over c1 and a reflected wave and a transmitted wave, if you eliminate the reflected wave, you'll, instead of getting the transmitted wave as a multiple of the input wave, you get a differential equation for the transmitted wave, a first order differential equation, which you can solve. And so that the transmitted wave depends on the incoming wave, but it's not as simple as saying the transmitted wave is just a scaled version of it, because it's not. So that's what happens if you put a mass on the boundary and you get this complex T, because there's a phase shift of the reflected wave. I would like to say in passing that I think students never seem to have any difficulty with understanding this boundary condition, the two strings stay joined together. They seem to have a lot more difficulty understanding this boundary condition, and this seems to me a very helpful way to think about it, that the difference in the slope provides the acceleration to the mass on the boundary. That's what you need it for. The mass on the boundary is moving up and down with the boundary, and that has to be accelerated, and therefore there has to be a difference in slope to do that, meaning that if the mass goes to zero, the slope is consistent. Okay? I think that's the most dynamically sensible way to think about that second boundary condition, which means that and it also prompts you to remember how to solve it when you when you have got a mass on the boundary. So when the slope when there is a discontinuity in the boundary condition. So what I wanted to talk about now was I want to talk about two very general ways of looking at waves. One is the Stokes relations, which do actually occur on the problem set, although only in passing. And the other is impedances, which are actually on the syllabus, and again they appear on the problem set. So I'll start with Stokes, because it relates directly to what we've just been talking about. So the Stokes treatment of waves at boundaries is very general, because it doesn't say what sort of wave's involved. It just says we're going to put an input wave with amplitude 1 to some boundary, and that will generate a reflected wave with amplitude r and a transmitted wave with amplitude t. So that's the actual situation. We're going to do a thought experiment. We're going to reverse time, and mathematically we do this by replacing t in the equations by minus t. And presumably that will produce an input wave on this side of the boundary with an amplitude t, and an input wave here with amplitude r, and that's presumably generating an output wave with amplitude 1. So the time reverse of this is an input wave, the time reversal of that is an input wave, and the time reversal of that is an output wave. But this second situation is clearly equivalent to input wave r producing reflected wave RT, so transmitted wave r times the transmission coefficient and a reflected wave r squared, plus an input wave T producing a transmitted wave r. Now, I'd need to know the transmission coefficient from the other side of the boundary. So this transmitted wave here will be T primed, and a reflected wave, and the reflection on the other side of the boundary is TR primed. And if I add those together, I've got to get this. So let's have a look at the outgoing waves on the left of the boundary. Here we have one, and here we have two outgoing waves. We have this one here, one equals r squared plus TT primed. And that's usually written 1 minus r squared equals TT primed. Okay? So that's one of the two Stokes relations. And if you just go back to the numerical example that we did yesterday, where we had r was minus a third, t was 4/3, and under the, was 2/3, and under those conditions t primed was 4/3, then this reads 1 minus a ninth equals 2/3 times 4/3, which is correct. So if we now look at the two incoming waves on this side of the boundary, now wait a minute, no, we have to look at the outgoing wave on this side of the boundary, because there's no outgoing wave here, but here there's that one and there's that one, and so we have to have RT plus TR primed equals 0, because these two have to add up to give no wave. Okay? So just by time reversing the actual situation, we've generated some very general relations between, here we can actually cancel the t, and it reads r is minus r primed, which was again something that we observed yesterday, but under these conditions r primed was plus 1/3, which is the negative of that. So that's applicable when the waves are unchanged in shape, when they're reflected and transmitted. So that would not apply to the equations that we've just derived, because in those cases we need to be a little bit more careful about how we do the time reversal. So the input wave is e to the I omega t minus kx. If I do time reversal, I will get e to the I minus omega t minus kx, which is not the standard form for the outgoing wave. The outgoing wave that I've been using is actually the complex conjugate of that. So if we need add the requirement to do a complex conjugate, then I get e to the I omega t plus kx, which is the standard outward going wave. So the combination of time reversal and complex conjugate is a rather better way to think of what I'm doing here. And so here I would want to put a star on that incoming wave and a star on that, which will put a star there, and no, not there. That would put a star on the R, and one of the R's there, so that would become mod R squared, and there'll be a star on the T and a star on the T. So what we get this time is the outgoing wave 1 has to be made up of the wave that's been the time reverse reflected wave, which is an R star, and then its reflected version, which is an R, which is mod R squared, and the time reverse transmitted wave, which is a T star, and then its transmission in the reverse direction, T primed. So that's a slightly more general version of the Stokes equation, where we've introduced a star in the first equation, and you'll see that it doesn't make, it's basically the same. But this version should be true of the equations that we derive from the equations with the mass on the boundary. So this version ought to be true even if the T's are complex. If I do the same if I just unpack the content of that, of course the modulus of the reflection coefficient is telling us about the amplitude of the reflected wave, and the phase of the reflection of the reflection coefficient is telling us about its phase. So if I just look at here, this is if I just look at the modulus of both sides of this equation, this side is actually real already. So the modulus of this side is exactly what it says, 1 minus R squared, and on this side that is mod T primed. Okay, so that's basically equivalent to the simple version of the Stokes relation at the top of the board there. But if we now look at the argument of this, which says 0 on this side, is arg T primed minus arg T, and therefore the other requirement that it imposes is that arg T primed equals arg T. Is that right? So T star. So the argument of this is arg T primed. The argument of that is minus arg T, and they have to and they multiply together, so they add. So that's right. Yes, arg T primed is arg T. So that's what the argument is telling us. Now, if we look at the second equation, we have we have to get no outgoing wave here, which requires R star T plus T star R primed R star T plus T star R primed equals 0. And last time we could cancel a T. Now we see that we can't do that. So that's the more general statement if they're complex. But again, if we look at the modulus of that, it says that modulus R is modulus R primed. Actually, let's just rewrite that slightly different. Let's put the equals there and a minus sign there. Okay. So then the modulus of T occurs on both sides of the modulus of that equation, which gives us mod R equals mod R primed. And then if we look at the argument of that, it says the argument of R minus the argument of R plus the argument of T equals plus or minus pi for the minus sign, minus arg t plus arg r primed. And so there's a relationship between the phase shifts on the two of the four different coefficients involved here. There are two relations between the phase shifts. There's one that says arg t primed is arg t. If we rearrange this for arg r primed, is minus arg r plus 2 arg t plus or minus pi. So there's a slightly complex relation, pun not intended, a slightly complex relation between the phases of the reflected coefficients. And all of those things will apply to the Stokes coefficients. Now this is a very general way of looking at waves, precisely because it only depends essentially on time reversal invariance. And so it applies to all wave situations where time reversal invariance is physically present, is a symmetry of the system. So it doesn't apply to waves where there are losses. So if there is energy being lost from the wave to somewhere else, so that the wave amplitude is actually decaying in space and time, then the time reversal, of course, is physically different from a wave travelling backwards. But as long as the time reverse situation is just physically equivalent to a wave travelling in the opposite direction, then this analysis applies. So it will apply, for example, in quite a lot of more complicated situations. So in the second year, you will do reflection and transmission of light waves at a glass-air interface. And that's a very three-dimensional problem because you've got the angle of incidence and the angle of transmission and the angle of reflection and so on and so on. But these diagrams, as long as you relate these to the three modes that are coupled, so the specific angle of incidence here, the specific angle of reflection here, and the specific angle of transmission here. If you look at the reflection and the transmission coefficients for those angles, they will satisfy the Stokes relations. It's a very, very general way of looking at waves, which is a useful check on whether or not you've got the right answer, and it's a useful thing to be able to look up. Another very general way of looking at waves is the concept of wave impedance. I noticed on the podium computer as I came in that in the last lecture you were looking at transmission lines. Is that right? You had a coaxial cable. You were looking at the inductance or capacitance per unit length of a coaxial cable. That's exactly where this nomenclature comes from, but I've stressed it's entirely general. So if a two-conductor electrical cable, which might geometrically consist of a central conductor surrounded by a hollow cylinder conductor, that's a television aerial, or it might consist of two parallel conductors held a fixed distance apart, and that's an Ethernet cable. Those are ways of, you can send signals down those, and the signals travel at the speed of light. And there are obviously two variables in play. So at any point, there's the current in one conductor. So you'd normally have one of these will be the signal line. In this case, it'll be the central one, and there'll be a return line around it. In this case, one of these will be the signal line, and the other will be the return line. The currents are always equal and opposite. So there's the current at any place x, which is obviously going to be called I. And then there's the voltage between those two conductors at that place, which is called V. So in this case, the wave has two different things which are interacting together to generate the wave. And that's quite a general state of affairs. And so we can always identify a V quantity which I'm going to call force-like, because V, of course, is potential. It's essentially any force per unit charge type of thing, or at least it's related to the electric field, which is force per unit charge. And this is basically current. This is basically velocity-like. And there are two equations that relate those together. So one is di by dx, which is, now for the fizz fills, I should point out the physics of this is absolutely not on the syllabus of this paper, but this is an allowable example, and therefore questions that appear mustn't relate to the electromagnetic physics of this, but they will relate, if they are any such, to the mathematics of what's going on. So I'm going to give these equations with the constants that they contain, and I'm not going to say anything about what they are. So this one here, di by dx, is c minus c dv by dt, and the other equation is dv by dx is minus q minus L di by dt. And so those are the the C and the L are usually called material constants. So they're just characteristics of the particular line that we've got, and when we apply these equations in other contexts, they will have other significances, and I'll give another example in a minute. So those are the equations. But if, for example, I differentiate this with respect to x and this one with respect to t, I'll get d2I by dx squared is minus c d2v by dx dt, and to get d2v dx dt, I multiply this equation by, I differentiate this with respect to t and multiply it by minus c, which gives me plus lc d2I by dt squared. And so I satisfies the wave equation with wave speed small c squared equals capital L capital C. This is 1 upon c squared d2 by dt squared, so it's 1 over LC. Obviously, there's symmetry between these two equations. I could just as well eliminate V, and V also satisfies the wave equation. So the waves propagate in this system, and that's the speed that they propagate at, and the waves satisfy the wave equation. So let's put in a solution. V is some forwards going wave, V plus, of t minus x over c, and I is I plus times t minus x over c. And let's put that into one of those equations. It doesn't matter which one I use, because the combination of the two of them just generates the wave equation, and this is a solution of the wave equation. So I'll just put it into the first equation. So I need to do di by dx, which is minus 1 over c I plus primed, equals minus capital C dv by dt, which is v plus primed. And so I get I plus primed equals, the minus signs cancel, cc v plus primed, and integrating I get I plus is cc v plus. And that is normally written v plus divided by z, where z is the wave impedance. Okay? And obviously, if you rearrange this, that says V over I equals Z, or V equals IZ. Z is like a resistance, and which is why the nomenclature has the form that it does. That is a wave impedance. And so the way you get a wave impedance is if these two quantities that are oscillating in the wave are always proportional to each other, then the constant of proportionality of the force-like quantity divided by the velocity-like quantity is a wave impedance. So if we put in our formula for C, that is Z is 1 over CC, which is 1 over C times the square root of LC, which is the square root of L divided by C. So the two material constants L and C, between them define the wave speed, 1 over LC, and the impedance, root L over C. So that gives us an entirely standard solution which we can apply, which says V equals V plus and I equals V plus over Z. If, on the other hand, we'd substituted a backwards going wave here, then the time derivative that I got, the time derivative was on the V side, the space derivative, we'd have a plus sign here, t plus x over c. So the space derivative, which with respect to I, would have the opposite sign, and the algebra would work through that we ended up with V equals V minus, then I is minus V minus over Z. So the relationship between voltage and current is reversed for a backwards going wave. And so there's an entirely general solution, which, because remember all the equations are linear, we can always superpose solutions. So in general, V is a forwards going wave plus a backwards going wave, and I is 1 over Z V plus minus V minus. And you can apply that general solution to any of these waves for which you can define a V-like quantity and an I-like quantity. So let me give you one other example, and there are two more, or possibly just one more, I can't remember, on the problem set. But this is sound waves. In particular, plane sound waves, because I want this to be one-dimensional. So these sound waves are going to be infinite in extent in the transverse direction and just propagate along the x-axis, so that the whatever, I mean, as you know, a sound wave is an alternating compression and rarefaction of the medium, for example, the air. But that's constant on planes transverse to the wave direction. So it's a one-dimensional wave. So nothing depends on the transverse direction, only on the z direction. The only difference from the waves that we've been looking at is that it's essentially longitudinal rather than transverse. And that messes up the energy calculation slightly, and I won't go into the energy. In fact, I haven't discussed energy here at all, but it is another example of this. So what are the two oscillating quantities in a sound wave? One is clearly the pressure in the medium. That's a force-like quantity, obviously, and the other is the velocity of the element of the medium oscillating forwards and backwards. And they are related, so there's an equation of motion for the medium itself, which is, I'll call that longitudinal velocity u, du by dt, and that's, so rho is the, well, strictly speaking, rho 0, that is the density, that's the background density, strictly speaking. So that's the density of the background state. I mean, the density is also oscillating slightly, but that's just the background. So this is a linearized version of this equation. There are other terms involving the change in that density, which I'm ignoring. And that's equal to minus dp by dx. And there's another equation which expresses conservation of mass because as the mass moves, as one mass moves forward relative to the mass in front, the density goes up. The increase in density causes an increase in pressure. And so there's another relation. And I'm not doing the physics of this. You will do this in the third year, but I'm just showing you how the equations work, which would be du by dx is minus kappa dp by dt, and this is the compressibility. So obviously P is a force-like quantity, and so I'm going to call that V. U is velocity-like, so I'm going to call that I. So these two equations read di by dt is minus 1 over rho naught dv by dx. Now where are my equations? Where are my standard equations? Di by so this is I want dv dx is minus L di dt. So in fact I had it in the right form to start with. I just needed to flip the terms the other way around. Di by dx is minus rho naught. The equation I'm trying to reproduce is di dx is minus, is the second one, is di dt, yes, di dt on the right. So I want dv dx is minus L di dt. Dv dx is minus L di dt. Yes, so I just need to write that equation down the other way around. So di by dx and dv by dx is this one here, which is minus rho dt. And I've defined the compressibility wrongly. The compressibility, that's an inverse compressibility as it stands there. That should have been a 1 over kappa. So there is a. So we get equations in the canonical form, but with slightly different constants, for the material constants, and obviously that is going to give us, so this is like C, so C is equivalent to 1 over kappa, and L is equivalent to rho naught. So the wave speed, the speed of sound squared, is 1 over LC is kappa over rho naught, which is the standard form for the speed of sound. So, so this approach of using impedances is extremely valuable because as soon as you've identified what the two oscillating quantities are, the force-like quantity and the velocity-like quantity, and how they're related by first-order equations, you can then identify the material constants, and you can immediately write down the wave speed. You can find the wave impedance. So the wave impedance for this, for a sound wave, Z is root L over C, which is root rho naught kappa. So if you then look at reflection and transmission of sound waves at a boundary, all of these boundaries will have the same form. The conditions at the boundary, unless you've got something complicated like this mass going on, but at a simple boundary where you've just got an abrupt change from one medium to another, like a sound boundary between air and a brick wall or something, then the condition is that V is continuous and I is continuous, and so you can immediately write down V is V plus plus R V minus, I is I plus minus R, is V plus over Z minus R V minus over Z, and here we have V is T V plus, and here we have I is T V plus over Z. So we just have an input wave and a reflected wave and a transmitted wave, and then if we just equate we set the coefficients, we set the coordinates to the boundary and equate, make the V's continuous, we can immediately work out the relationship between V minus and V plus and the transmitted wave and so on. So you get a perfectly standard form for the impedance, for the reflectivity in terms of the impedances of the two mediums. So this would have to be Z1 and that would have to be Z2, which throws up the fact that what matters at a reflection is the discontinuity in the impedance. That's what drives the reflection. And so the impedance, although it's introduced here as a rather formal quantity, it gets to become, if you use this method a lot, a significant physical parameter for the waves. So it is kind of on the syllabus. I've never seen any question that referred to it. It now has a brief appearance on the problem set as well. So I've kind of finished talking about waves. We've really only done three things with waves. We've solved the wave equation using travelling waves. We've solved the wave equation using standing waves. We've looked at the transport of energy in the waves, and we've looked at what happens on boundaries, and that's really all that the syllabus consists of, and it's fairly straightforward. So at the end of the lecture course we have prizes. So you all deserve a prize having stuck it to the end, but I want to make two special mentions of the gentleman in the second row who's always grinning, which I find enormously helpful, and the lady who asked a question about my dog. Thank you very much. If anybody wants to ask any questions, I'll be sticking around to answer them if necessary.